summarize how it looks like, or will you give us the shapes?
Are you talking about the polar graph stuff? The
Yeah.
polar functions? Okay, great question. Okay, so we're officially recording now. So with the polar function stuff, in the fall, you will need to know the graphs. So like if they call out like, you know, r equals like 3 cos theta, like you need to know what that looks like. You need to know like the bounds and so on and so forth in the fall. But for this class, I think either I'm just going to give you the graph and you should be able to figure out the bounds through the graph, or something else, if that makes sense. So when in doubt, honestly, when in doubt, just start plugging in theta values and ask yourself, okay, what's going on at this point? And then what's going on at the next point? And then that should kind of tell you like the direction. Like, so for example, if I wanted to figure out this guy right here, right? I can plug in 0 and I get, what is that? Cosine of 0 is 1 times 3. So this means at angle 0, when you're like on the x-axis, you go up 3. So it starts there, right? Then I plug in another point. Let's say like, I don't know, pi over 2, pi over 4. Let's go pi over 4.
Square root of 2 over 2. It's better pi over, yeah, 3.
So it would be cosine of pi over 4, which is root 2 over 2.
Square root of 2 over 2.
So 3 root 2 over 2. Right? So let's see, root 2 over 2, that's like 1.4. So times 3, it's like that. It's like 3. So it's like, so we know that when you go to pi over 4, right? The radial length is like about like 3-ish, and I don't know. That just means that you know it's going in this direction, right? And if I were to give you the picture, it looks like this, right? So that should kind of tell you, right, that you are going in this direction. I hope that answered your question, Joy.
Yeah, it did. Thank you.
Awesome. Whew. All right, so let's get started here. We are recording, right? Let's talk about that quiz. I left you guys, well, so if you submitted on Canvas on time and stuff, you should have your quiz back. If you emailed to China, I don't know what you got. I hope she updates it. I don't know if she's still working on it or whatever. If you haven't taken the quiz yet, I'm just gonna give you until Wednesday to take it, because it should not take you more than like about a week to make up the quiz that you were supposed to be responsible for. If you were absent for whatever reason, you were notified to make up your work and stuff like that. I can't wait past the midterm for you to take a quiz that you were supposed to kind of set up with like either China or myself. So I think I'm just gonna call it by Wednesday. If it's not in, it's not in. Okay? If you have issues with that, you gotta let me know. Once again, you gotta communicate with your teacher, like any issues that you guys have. Does anyone want to say anything to that, or does anyone have any questions about that right now? About the quiz number 1? Okay, once again, just message me, all right? The average of the ones that I graded, if you haven't heard, it was about a 61%. So they weren't good. There were a couple of people that I may need to reach out to, because some of the work was kind of it was concerning, some of the work. But most of you did well or did okay. Like I can tell by like looking at your work, like if it was like genuine in terms of like you actually did try and like you were using the stuff that we talked about during lecture and things like that. If I saw some like foreign things on there, you know, to a point, I was like, all right, this is kind of questionable here. I'm not really sure if they're paying attention during lecture. I'm not really sure what they're doing in their spare time. Maybe you need to study more, you know, go through the lectures again, or parts of the lectures, or watch those supp videos, or go to office hours, or whatever, you know? So if that's you, please reach out, get some help, all right? All right. And yeah, that's it about the quiz. We got a midterm on Wednesday. So it's gonna follow the same format as the quiz, except there's no review in the beginning. As soon as class starts, if you're late, you're late. I'm gonna give you that 10-minute window again at the end to submit and stuff. But other than that, if you're not there, or if you're not excused for whatever reason, you will probably take the 0, I guess, right? Because I'm making it very clear. It's going to be very similar to the quiz in terms of like the format and stuff. I'm still figuring out some problems. I'm like taking in some in and like putting some out, and because I have to like redo everything. So, but right now it looks like the midterm is about like 7 problems, with some have like parts and some have less parts. Okay. So yeah, if you guys will probably take tomorrow to review, or a huge chunk of tomorrow's recitation to review. All right. What we're doing today, 10-1 and 10-2, is not on the midterm. Okay. What we do today, 10-1 and 10-2, is not on the midterm. So please don't worry. Like, don't freak out if like the stuff today is kind of difficult, but it is on your next quiz. On the next quiz. Okay. And you guys should know when the next quiz is. It is the 21st, which is next Tuesday. All right. So I would take tomorrow to really focus on studying for the midterm. All right. Not as much time to review the stuff we do today. Okay.
So it's the same as the last time, and chapter 11. That's it.
Oh, yeah. So in terms of topics, yeah, it's everything. So everything from chapter 6. So like area, rotations, everything from chapter 7, which is the integration techniques. Everything from actually, I don't think there's a differential equation on there. There is a logistic growth, but no, like you have to split the variables and solve. I think I took that one out. And then there's polar coordinates. Okay. Any other questions about the midterm? Did you guys get that down? Did you guys write that down? I really hope you guys wrote that down. So once again, chapter 6 is fair game. Chapter 7 is fair game. 9-4 is fair game. And then chapter 11 stuff is fair game. We good? We good? No homework due tomorrow.
Yeah.
So I don't know, according to China told me that she didn't assign homework during last recitation intentionally. So you guys got lucky. I wanted her to assign homework, but she was like, no, I think it's better this way. So I was like, okay. So yeah, so please study. All right. Yeah, let's get started, guys. Let's you guys ready to learn chapter 10, dive into sequences and series? I hope so. Can you guys give me a thumbs up and let me know that you're still there?
Thumbs up.
Some of you guys don't have thumbs up. Okay, all right. Okay, all right. So let's just jump right into it. Man, this is it. This is like winter is here. We're diving into sequences and series. All right. This is like the latter part of Calc 2. I don't want to say it's the latter half. I want to say maybe like the latter third or so of the course in the fall. It is a huge part of Calc 2, and in fact, it's probably the reason why so many people believe Calc 2 is harder than Calc 3. I don't know if you guys have heard that yet, but a lot of people claim that Calc 2 is harder than Calc 3. I disagree. I think Calc 3 is much more complicated than Calc 2 for so many reasons. But so I think it also depends on your fundamental like kind of knowledge on series. And 10-1 talks about sequences. Did I spell it right? Yeah. Sequences. 10-1 talks about sequences, which is like the basic building block of series. If you don't understand sequences well, you're not going to understand series well. You're not going to understand the later stuff well, and so on and so forth. So it is important that we kind of like understand sequences relatively well. Okay, so let's get started with basic sequences. If you guys don't know, a sequence is just I don't know. It's in layman's terms. It's like a string of numbers represented by a rule. I feel like that's like the easiest way to kind of like explain it. They're separated by commas, okay, because it's a string of numbers. It's just like a pattern of numbers, okay. The book kind of uses a more fancier definition for it. They call it a sub n, okay, is equal to f of n, right? So a sub n is equal to f of n. This is the notation. You're going to see this a lot, this a sub n. That just means a sequence. Oh, and by the way, n has a special word name for it too. It's called the index. Okay, and what they're saying here is you can treat n as almost like a function. I'm sorry, a sub n as almost like a function where your input is n, right? So it's like you can think of it as like you know, you're plugging in n values, but the n's are sequential integers. What does that mean? It's just not like no decimals. It's just 1, 2, 3, 4, 5, 6, 7, 8, all the way to infinity. Okay. You normally don't deal with negative numbers for inputs, but you can. It's up to you. It depends on like how the sequence is defined. All right. There are some examples that they give on page 554. Page 554. Let me share my screen. So if you guys can see, right? So those are some examples of sequences, right? They give you, notice they give you like a specific domain, right? A specific number to start with, and then the outputs of the sequence, right? Notice they're all separated by commas. Yeah? Am I going too fast? Can I go faster? Am I going too slow?
Yeah.
How you guys doing?
Good. Yeah.
Good.
I remember the sequences and everything in half one.
I mean, normally you don't go through sequences.
No, like it's that explicitation, explication, and everything. It's
okay.
And like the different rules and everything to find out the rate of change, not rate of change and everything, but like how it's changing during the whole sequence and everything.
Right. Okay. So yeah, so that's the basic idea of a sequence. And if it's defined like this, normally it also has, it's called explicit. It's like because there's an explicit definition. There's an explicit way for you to plug in an n value and it'll spit out that term. Like, so like if I were to say a sub n is equal to 1 over n plus 1. I don't know. I just totally made this up. Notice I have to give you an n value to start at, right? So if I were to say, find me the 50th term, because this is an explicit definition, I can just plug in 50, right? And get an answer. I don't know exactly what that numerical answer is, but I can get a specific answer in the sequence. Does that make sense so far? The book then goes into something called recursive sequences, and this is something you'll see. This idea of recursion also appears in like your MATLAB courses, computer programming, and things like that. It's how a lot of programs work. Maybe not as efficiently as it could, but it does define like it is interesting to see like the backing of it, like in terms of sequences. So recursive sequences are sequences that basically they call themselves within the sequence. Okay, so it's like a sequence that calls its own rule and has it apply it over and over and over again, depending on what input you're specifically looking for. Right. And another key thing about recursive sequences is it must always give like a starting point or a value. Has to always give a starting point or a value. All right. Meaning like they have to tell you what the first term is, or like the nth term or whatever, right? They have to tell you what that specific term is so that you can apply it to the rule and spit out the next one. Okay. So a really good example of this that is really common, so I'll call this example 2, is Fibonacci sequence.
4x.
I'm sorry?
4x. No, wait, no, now look at it. I remember. 4x.
Fibonacci sequence, I don't know what you're saying, Lemek, but anyways, Fibonacci sequence is, it's a very, very common sequence. And in fact, the whole like golden ratio, I don't know if you guys ever heard of that either, but there's something called the golden ratio. It actually comes from this Fibonacci sequence as well. I don't know if you guys saw that, like there's a picture, I look at math memes sometimes, like there's like a Fibonacci pigeons, and they were like pigeons that were like separated by the Fibonacci, I don't know. Anyways, so Fibonacci sequence, it goes like this. They use F for Fibonacci, of course. They say F sub 1, meaning the first term in the Fibonacci sequence is 1, and the second term is also 1. And then the third term, or I guess every term after that, right? So they're kind of saying like F sub n is equal to, you take the n minus 1th term and add it to the n minus 2 second term, right? So it's basically saying you take the 2 previous terms and you add them together. So what would this look like? Right, it would be 1, 1, and then you add 1 and 1 to get 2. You add 2 and 1, you get 3. You add 3 and 2 to get 5. You add 5 and 3 to get 8. You add 8 and 5 to get 13, and so on and so forth. Anyone watch Devs by any chance? Did anyone watch that or no? Am I the only one? Okay, never mind.
Can you repeat that?
There's a show. It's called Devs on Hulu. It's they had a Fibonacci reference in it, which was really funny. But yeah. Anyways,
Too rich for my blood. I don't know.
It's about like programming, but like in a crazy. It gets crazy. It's only 8 episodes long. It's like very cinematographically good. I don't know, or whatever. Anyways, so yeah, that's the Fibonacci sequence. But like as you go on and on, if you take the limit as n goes to infinity of our Fibonacci sequence, it starts to approach this 1 plus root 5 over 2, which is also 1.618, so on and so forth. It is, oh gosh, that is not phi. Sorry. It approaches this guy. It's called phi. It's another Greek letter. It's another constant that appears in life like pi or e and things like that. But yeah, phi is like the golden ratio. It appears everywhere. It's so cool. It's like the number of spiral arms in a sunflower. You know, it happens in flower petals, like the shell of a nautical thing or whatever. Hurricanes. There's like proportions in your body that appear. Like it's really, really interesting stuff. If you guys ever want to like, if you're ever bored one day, you know, just look it up. Look up golden ratio, and it appears everywhere. Anyways, sorry, that had nothing to do with today's lecture. Let me move on here. Let me do like a real or an example that you'll come across in the class. So let's call this example. What are we on? 3, 2, 3. 3. This is on page 554 in your textbook, the PDF. And so they're saying a sub 1 is 1. A sub n is defined as 1/2 a sub n minus 1 plus, 2 over a sub n minus 1. So you can see in the definition, I'm not actually going to do the problem because I feel like it's going to take too long, but you can see within the definition, you see the a sub n being called again, right? It didn't have to be a sub n minus 1. It could have been a sub n minus 2, but then what would they need to give us if they did that?
They'll need to give us the original position.
They would need to give us like the next one. They would have to tell us what a sub 2 is if they did a sub n minus 2, because you can't find like, you can't find a sub 3 without, oh wait, no, actually, no, you could. Never mind, sorry, I take that back. Or no, you couldn't find a sub 2. Okay, the point I'm trying to make here is where you start is really, really important, right? So for this one, right, and like I have to tell you that n is going to start at 2 because they give us 1. Does that make sense?
Okay. Yeah.
Right? So like in order to find the second term, I have to use a sub 1. Whoops. I have to use
Oh
a
yeah.
sub
So
1
they, yeah, okay.
within the
So they couldn't
definition.
start at 2 because they didn't give us the term before 2. But,
Yeah. So
yeah.
if they didn't give us, if they did not give us a sub 1, we would not be able to find a sub 2.
Yeah.
Do you see what I'm saying? So it's like it's going to repeatedly call itself. And if I wanted to find, so this is one of the downfalls of recursion. If I wanted to find, like, let's say a sub 100, think about that, right? That would mean I would need a sub 99 plus 1 over, what is it, 2? 2 over a sub 99, which means I would need a sub 98, which means I would need a sub 97 and 96, 95, 94, 93. I would have to compute all of that in order to get to a sub 100. Do you guys see? That's like, that's the downfall of recursion. It takes too many steps to do when you get to higher values of n. But for like computer purposes, this is actually something a computer can do relatively easy, right? So like recursion, that's why you see a lot of recursion in like programming and like the computers and stuff like that, as opposed to like practical like math problems, right? All right, so let's move on to some calc related stuff, right? Because you know, we now have an idea of what a sequence is. Let's start applying some calc to it, yeah? The next part of this section talks about taking limits of a sequence, all right? And great news, the rules for limits of a sequence actually, I'm sorry, the rules of limits of a function actually follow down to sequences. So what am I talking about? Like, do you guys remember these rules? Like, I don't know, f of x plus g of x is equal to the limit as n goes to, I shouldn't use infinity, I should use like a value. A of f of x plus limit goes to a of g of x. I hope this looks familiar.
Yeah.
Maybe, yeah. Right? It's like, it's saying how like addition and subtraction, I forgot subtraction, is preserved under limits. That's the way you say it, right? Same thing with multiplication, right? If you're multiplying two functions, you can kind of break them up into two limits, and then division, so long as the bottom isn't 0. So like, so these properties actually kind of follow sort of with limits, all right? And what this means is we can also apply a calc thing, L'Hopital's, to sequences. Whoops.
Okay.
Sequences. And that kind of opens up some like easier ways to kind of solve problems. Just yeah. So they have. Okay, so I'll tell you about it because your professor might pull it out and like do it in the fall, and it's kind of it's annoying. But on page what is it, 555 in the PDF, there's a proper definition of a limit, and I guarantee like 90% of you have never learned it this way, but it's called the delta epsilon proof of limits. Some of you may have heard this. I'm just curious, can anyone, if you heard of it, can you like raise your hand or like put something in the chat? Like, oh, I've heard of the delta epsilon limit thing. No, nothing. Crickets. Okay, never mind. So yeah. Oh, I see a hand. Oh, Handel. So yeah. There's this really. It's not complicated. It's just a more like formal way to prove what a limit is using like a definition. If you're interested, you can look it up. But you know, I'm not going to really test you guys on that. All right. So why don't we just talk about this other theorem? You know what? No, let me just do a quick example with you guys with proving. I mean, finding the limit of a sequence. Okay, so this is example. I think it's 4. We're on page 556. All right, so let's say I give you a sequence. Looks like this. Comma 3 squared minus 2 squared. Comma, oh, that's a 3. Sorry. 4 squared minus 2 over 4 squared, comma 5 squared minus 2 over 5 squared. So notice I didn't give you what the general term is, right? But this dot dot dot, right, tells you that this goes in this order, like forever, indefinitely, right? So what do you guys think? Like, how could we find the limit as n goes to infinity of a sub n, if a sub n is defined as such? What do you guys think? Like, what do you think we should do?
We could find the explicit rule.
Yeah. So
find the rule and then you put it to the limit.
A big part of sequences in series is pattern recognition. So, however many, terms it takes, everyone's different, right? Some people saw it right away. Like some people were like, oh, I didn't need that 4th term, or I didn't need that 3rd term. Like, I think I could see the pattern right away. Some people need that 4th term, 5th term, whatever. For you, you just do as many as you think you need. Okay. If you're like, I'm still not sure, let me figure out the next term, do it. Okay. Don't feel like you need to prove anything or anything like that, right? So if I were to write the next term, it looks like the next term would be, 6 squared. It looks like
minus 2 over 6
2
squared.
Is constant, yep, over 6 squared. And I see that the only things that are changing are these 2 pieces, right? Everything else looks like it stays the same. So if I wanted to figure out my a sub n, it looks like I have n squared minus 2 over n squared.
Yeah.
How you guys doing? Is that all right?
And now you find the limit.
Well, now we want to find the limit, right? So you have to write the limit operator signed, okay? Please do not say goes to and then like your answer. Okay, that is not sufficient work, especially in college, right? That some of you guys kind of did that on the quiz, like we're doing shortcuts with your work. If you're not explicit with your work, I can't give you full credit. All right, that's just how it is. Okay, so please don't do that. What we're going to do is simplify this. And in fact, I'm going to show you a trick that maybe some of you already know or some of you don't know. But what I'm going to do is I'm going to rewrite this by dividing everything by the highest power. You guys catch that? I'm going to divide everything by the highest power. So it looks like my highest power is squared. So I'm going to divide everything by n squared. So my a sub n is equal to 1 minus 2 over n squared all over 1. Do you guys see how I did that?
Yeah.
I'll write it out. So over n squared, and I'm allowed to do this, right? Because the value of the quotient is still the same. So clean this up a little bit. 1 minus 2 over n squared. And now we can apply the limit as n goes to infinity of a sub n. And you treat this like you normally would with any other limit, right? This goes to 0, leaving you with 1. Pretty easy?
Yeah.
Like I said, it's almost like limits, the same limits that you learned in pre-calc and I guess calc, but we're kind of going to make sure that our work is a little bit more explicit this time.
John, is proving this, is there the other way to prove this? Like, has there been examples you've seen that use like delta x, if that makes sense? Like, you know how it's n squared? Have you seen examples where it's like delta x squared minus 2 over delta x squared?
I mean, if that was the case, then you still get the same answer.
Okay, yeah. Because I think I realized like I've seen this before because it makes sense now.
Delta x, I don't know. That could refer to a lot of stuff, man.
Yeah, I think in the example I was taught like proving it, the teacher had used delta x, but
okay. Oh, I know what you're talking about. You're talking about the I think the formal definition of a derivative. This thing.
I think, yeah, it was something like that. Yeah.
Yeah, that's the formal definition of a derivative. That you learned that in calc, or in the beginning of derivative.
Yeah.
Let me show you one more example, then we can move on. I'm running out of time here. I'm going to show you a L'Hopital example. Oh, snap, I gave it away. Damn. Limit as n goes to infinity of n plus ln of n all over n squared. So once again, pretend that this is a sequence, right? You're given a sequence, and you want to know if this sequence converges or diverges to a specific value, right? Or I guess converges to a specific value, right? Oh, I'm sorry. So for that last example, you could say a sub n converges to 1, if you wanted to, because we're going to be throwing around the word converge and diverge a lot in this chapter. So in this one, right, I guess you could just right away let n go to infinity. I don't know the best way to do this. Yeah, okay, no, we can just let x go to infinity, and we get what? It looks like infinity over infinity.
Yeah.
Right. So this is indeterminate. If you are going to use L'Hopital's rule, and I'm going to make this very clear, if you are going to use L'Hopital's rule, you have to show this step. You have to show this step. Why? Because L'Hopital only works on indeterminate forms. If you were to get like infinity over 0, wait. Yeah, if you were to get infinity over 0, that is not an indeterminate form. So that is not L'Hopital's. Like you cannot use L'Hopital's in that. Okay, you guys need to check for indeterminate form. Okay, so we use L'Hopital, and we get 1. So use L'Hopital. You guys are familiar with L'Hopital's, right? I know some teachers may have skipped it because of the quarantine and stuff. But if you guys don't know what it is, definitely look it up and learn how to do it. So you use L'Hopital's, you get 1 plus 1 over n in this case, over 2n. And what do we get here? It looks like 0, right? Because this goes to 0, and this is going to keep on growing. So you're like 1 over like 2 times something that grows incredibly large. So it looks like 0. So the sequence converges to 0. How are we doing? You okay? Any questions so far?
Hopefully. Oh yeah, wait. So just to make sure, what you said before, like my AirPods died and everything. But so when we're doing something like a quiz or a test and everything, show that it's indeterminate, and then move on. So we can't just like put equals and then just automatically use the El Hospital.
Yeah. So so you can't do this. Okay, look, this is a no-no. All right, please. If you're not listening, listen. No, so don't do this. What was it? N plus 1 over n squared. Right? You cannot do this. That's not sufficient work. I don't know how you got that. You know?
Wait, no, not just equal to 0. I'm talking about like equals to limit n approaches to infinity 1 plus ln over 2n.
Oh
like
yeah. Think about it. You can't do that either, right? Because those are 2 different arguments.
Yeah.
1 plus ln. This is not a true statement. You can't say that they're equal because they're not.
Okay.
So the only way you're allowed to use L'Hopital's is to show the indeterminate form. So please don't do it, okay? It doesn't make sense in the flow of your work. All right. I'm just gonna mention this. I'm sorry, I'm going all over the place because I want to get to the series. So the last thing, there's something called Theorem 4 on page 559. It basically says that limits are preserved under functions. In fact, continuous functions. So it says if f is continuous and the limit exists of a
I remember these.
Then limit So n goes to infinity of f of a sub n is equal to f of okay. So what this is trying to say is that limits the action of a limit, right? Because limit is an operator, right? And you guys know what operators are, right? Operators are like when you square root something, or like when you tan inverse both sides or something like that, right? Limits are operators that actually can move freely within within the function, within any operator, right? So like if I had the limit of a root, I can actually bring that limit inside the root if I wanted to, if it made the computation easier or possible, right? Or if I had a limit of like e to the x, I could take, or I'm sorry, a limit of e to like the n, then I can take the limit upstairs into the exponential part too. Does that make sense? I hope that makes sense. Same thing with logs. I can take a limit inside a log or outside a log. It can move freely. The definition won't change. All right. Okay. How you guys doing? You guys good?
Good.
Can you
Yeah.
give me a thumbs up? Tell me that you're still there and listening and not sleeping or watching anime. All right. That's some of you. No, Alvaro, you're awfully quiet. Okay. All right. Let's move on to. I guess I should talk about this. You know what? No. I'll mention it. I'll mention it. Okay. There's something called. Whoops. There's something called the squeeze theorem, and it is a useful tool. You're not really going to need it for this class, but it might pop up. I'll just mention it. It's on page 515.
The comment.
I will rejoin the call. I don't know why, but something happened to my computer and I can't hear you guys clearly. Okay, I'll let you in. There's something called squeeze theorem. It's pretty interesting. Definitely look into it. I'm not going to put it on the video or anything like that, but you should definitely look into it because it is a useful tool to know.
John,
Yes.
is that the one where like you squeeze a function between two other ones to get the limit?
Yes.
Or is that different?
It is the same. It's the same idea, right? Because once again, we're not dealing with functions, we're dealing with sequences. So like it kind of like it follows with sequences also, right? If you have two sequences that you know and they both go to the same thing, then any other sequence in between those two sequences will also go to the same thing. If that makes sense. I know I kind of said that really quick. But yeah, definitely look into squeeze theorem. It is useful. And I think that's it for 10.1. They do monotonic stuff. Don't worry about that. I'm just gonna skip that. Yeah, that's it. I think that's it for 10.1. Awesome. I'll do that one in the video. I'll do something else in the video. Let's move on to 10.2. So 10.1, once again, the recap is, you got to know what a sequence is, how to define a sequence, how to recognize the pattern, and how to take the limit of a sequence to tell if it's convergent or divergent. Is that okay? I'll do an example of like more limit examples in the video, in the supplementary video. So let's move on to 10.2. Now that we understand, or quote unquote, understand sequences, we can kind of jump to series, which is slightly different than sequences. So this is titled Summing Up Infinite Series. Summing up infinite series. So this is it. This is the only difference between sequences and series. And it's such a small difference that I think this causes a lot of people to kind of get them mixed up all the time. It's a very common thing. People tend to mix up the rules for sequences with series, and it kind of causes problems sometimes, especially when talking about convergence and divergence. All right, so let me just kind of state it now so that I can say I said it. Sequences versus series, separated by commas. Series is separated by addition. That is the only difference between sequences and series. And what that does is it causes slight differences in how you approach these problems, right? With series. All right. So sequences are separated by commas, right? It goes term by term, tells you what it's going to like tend to, but then as soon as you start adding up those terms, it kind of changes the rules slightly. All right. I'm gonna skip that. It changes the rules mostly with the convergence and divergence stuff. So let me I'll do that in the video. So I have my notes like behind you guys. So yeah. So let me kind of like explain what I mean by that with an easy example. So let's call this example, I don't know, 5, I think. Right. I'm going to look at.
John, can you scroll up real quick? Sorry.
Not my fault.
Thanks. All right, I'm good.
All right. So I'm going to look at this sequence right here. How do I know that I'm playing with a sequence here? There's no summation sign. Okay. So that's the dead giveaway. So, I have to tell you, starts greater than or equal to 1, right? So I'm going to say this versus, which is, so this is a series representation of the sequence, right? I just took the sequence part 1 over n and I put a summation sign in front of it. And once again, this is the index, like this, and it tells you where it starts, and then the top number is where it kind of goes to. In fact, that should kind of look familiar, right? With integrals, upper bound and lower bound. You can call them upper bound, lower bound. I'm sure it's fine. But look, here's the difference. If I take the limit as n goes to infinity of a sub n, what do I get? It's an easy one. What happens when n goes to infinity of the sequence?
0.
Yeah, right. It's going to go to 0, like meaning the terms, term by term, is going to go like 1 over 1, and then 1 over 2, 1 over 3, 1 over 4, and so on and so forth. And then it's going to eventually get so close to 0, it's pretty much 0. Does that make sense? Right?
Yeah.
But the difference here is I'm not doing that with the series, right? With the series, what this means is I'm doing 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so on and so forth.
It's going to get to infinity?
Well, I'm not going to prove it yet. We're going to prove it in the next lecture or so.
Okay.
But this actually does not go to 0. This is actually going to diverge. Okay? So this is a very common example of when a sequence does something and the series does something else. Does that make sense? This is the point I'm trying to drive here. Sequences are not series. They're like related, they're used in series, but it's like when you're talking about convergence and divergence, different things can happen. John, does that mean that, they're all going to do that? No. There can be some examples where they both do the same thing, right? But it's like, it's the counter examples that we're kind of more interested in because like that's going to help us with defining what a series is. Okay, I'm going to jump to geometric series because everything else I'm going to just do in the video. There's in the video, I'm going to talk about something called telescoping series. And that's going to be like another example of a series that actually converges. Wait, no. Converges? No, I think it's going to, never mind. Sorry. That example, both examples are going to, the sequence and the series are going to converge, but it's going to show you how to sum up a series.
Okay.
Okay. Because I don't think we know how to do that yet, right? How do we add up an infinite amount of terms? It doesn't make sense, right? Mm-hmm. So I'm going to do that in the video. Okay. And that's probably not going to be on your final exam or in this class, but it is going to show up in the fall. So it is.
There's a question in the chat.
Oh, I'm sorry. So do series have more specific answers? Yes, yes. We're gonna do that with geometric series in a second. Okay. So let's move on. Any other questions so far?
Good.
Ron, I just had a quick question.
Yeah.
Could you tell us what the answer for that series going n to infinity would be? Would it be like 2?
N to infinity. Are you which one are
I'm
you talking
the
about?
right side right now on the
This
screen.
one right here?
Yeah.
I
What
said
would
it. I said it diverges. Diverges to infinity.
Oh, with that.
Meaning, when you add it, it's gonna just go up to infinity.
Oh, okay.
I know it doesn't seem like it, right? Because you're adding fractions, but it does go to infinity. In fact, it's like it's a very special case. I'm getting too excited. Never mind. All right, but we'll talk about it later. All right.
All right.
All right. So where are we? We are talking about geometric series now. So. Some of you guys may be familiar with geometric series because you may have played with them a little bit, but we're going to go a little bit more in depth with it here. And I'm actually going to come up with the formula for how to sum up a geometric series. All right, you guys ready?
Yeah.
Great. Geometric series. What is a geometric series? Well, it's a series. And it starts at some n value. Some start at 0, some can start at 1, but definitely pay attention to the starting value. I'm gonna say 0. I'm gonna say it starts at 0 for this one. Okay, so it starts at 0 to infinity, and they all have this form. Okay, they all have this form. It goes a r to the n, a r to the n power. If I kind of string this out, right? If I write out all the terms, so what do I get? If I plug 0 in, well, it looks like I get a. And then I'm adding the next term. If I plug 1 in, I get a times r to the first power, which is r, right? And then I plug in 2, I get ar squared. I plug in 3, I plug in 4. And hopefully you guys can see what's going on here. Like what's happening from term to term.
It's multiplying by r each term, yeah.
Yes. So we give r a specific name. It's called the common ratio. A is just the starting point. A is just the starting value. It could be like 5. It could be it's just a constant, right? So, but r is the thing that you're multiplying each term by to generate the next term, right?
Yeah.
You guys doing okay? Am I going too fast?
No, you're doing good.
Okay. All right. So with geometric series, right? Actually, with any series, it's only 2 things can happen with series. It either, when you add them up, it either gets a convergent answer, meaning like it'll be a finite value, or it diverges because you're just adding too much and it goes off to infinity. Does that make sense? There is no middle ground. There is no gray. There is no like in between convergent and divergent. It's like, oh, I kind of feel convergent, but I'm actually going to diverge. There's none of that. It's either convergent or it's either divergent, right?
Okay.
So that's an assumption we need to kind of make to kind of prove this next part. So we're going to assume that this converges, right? Because we're trying to figure out like the formula, like how to like sum this up, how to get a finite answer. Does that make sense? So we're going to assume that all this nonsense, when you add it up, you get a value, and we're going to call it S for sum, right? So watch, here we go. So I'm going to rewrite it. A plus AR plus AR squared.
Oh, I remember this.
Okay, plus AR to the 4 is equal to.
Okay, this is fun.
And in fact, this is going to go all the way to some really big number, right? The exponent. I'm just going to call it that guy right there. We're just going to stop at some n value. Yeah. And the cool part is you can actually do like algebra to this. I can multiply both sides by r. I can multiply both sides by r, right? So what's going to happen? All my terms are going to have an extra r on them, right? So I get AR plus AR squared plus AR cubed plus dot 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 ARN is equal to R times S.
Yeah.
So far so good. Now, since I have two equations here, I can kind of play with them, right? Like, kind of like, you know, elimination when it comes to solving a system, right? I can subtract 1 and 2. I can subtract 2 from 1, right? And what's going to be left is, if you think about it, right, if I subtract all of that, you notice that the kind of like the middle terms are going to cancel out. Do you guys see that? Like this is going to cancel out with that, and that with that, and that with that, and so on and so forth, and so on and so forth, until the one before AR to the n. So that gets me, looks like A plus AR to the n equals S minus RS.
Wait, isn't it A minus AR to the n?
Oh my gosh, who said that? Henry, thank you so much. Good looks. All right, yes, A minus. And just in case you forgot what we're doing, we're solving for S, right? Because we want to know what a converging geometric series, like what the sum is, right? So we want to solve for S. So let's use some algebra, right? So I'm going to factor out an S. Divide through by 1 minus R. And there it is. I have a formula for the sum involving A's and R's, right? Which I can figure out given a series. Yeah?
Yeah.
There's one last thing we have to do. Right? So like right now, the way it is, R can equal 1. And that should kind of make sense. What would happen? What would happen if I had a series that looked like that? What do you guys think? Oh, from I don't know.
The answer will only be 1. Yeah, the answer will only be if it's like 1 to the 0 powered 1, 1 to the second powered 1, 1 to the third powered 1, and just keep going on
Okay,
forever.
right. So what does that mean?
So it's going to
It'll
diverge
be
at infinity.
convergence to 1.
So, okay. So once again, if this was A sub n, this actually converges because it equals 1. The terms equal 1, right? The terms will always be 1, but the series diverges. Why? Because we're adding all of those ones an infinite amount of times. Do you see that? Yeah. So this is another example of the sequence converging, but the series actually diverges.
Okay.
Crazy, right?
Yeah.
Thank you. I saw the reaction. Thank you, Anne-Marie, for that. I appreciate that. All right. So what I'm saying is this is why we this is another reason why we ignore the one case. Okay. So what that means is we are actually going to look at okay, if the ratio was greater than 1, right? If I had like 1.5, what do you guys think would happen in that case?
That'll be a divergence.
It still diverges, right? Because you're adding 1.5 a gazillion amount of times, right? The interesting part is we want to look at the values in between 0 and 1. Right? We want to look at the fractions because those are the ones that are like, maybe they'll converge or diverge depending on what the fraction is, right? So if we're looking at those values, right? Sorry, hold on. If we're looking at those values, right, so we can sorry, I was cheating a little bit. We can look at 2 cases. When the absolute value of, oh my gosh, the absolute value of R is greater than 1, and when the absolute value of R is less than 1. This is what I'm saying, right? Because when it's 1, we know it diverges, so we don't really care about that case. But when it's greater than 1, right, Lamech just said it's actually divergent. When the absolute value of R is less than 1, or when R is in between 0 and 1, let's go back to our equation here.
Wait, I have a question.
Yes.
Like if we have a quiz or a test and it's and the R is greater than 1, could we just automatically put divergence, or do we have to go through the whole process?
I'm gonna explain that in a second, okay?
Okay.
Yeah, give me a second here. So what we're saying is, what happens when limit as n goes to infinity of this guy when R is a fraction?
When R is a fraction, that means that will go to 0. It'll converge to 0. Wait.
Okay. Does anything happen to the A?
No.
Okay. Does anything happen to the 1?
No.
Does anything happen to the negative R?
Yeah.
No. The limit is only affecting the n, right?
Oh.
So everything else stays the same. What we're looking at here is this guy, this piece right here.
I thought the R is gonna. Okay, I understand now.
Okay, so when R is in between 0 and 1, right?
Mm-hmm.
That means, and I'm sorry, and we take the limit as n goes to infinity, what happens to the highlighted area? What's going to happen to that? As
When
n goes to
goes
infinity
into
of a fraction.
that is also going to go into infinity. Wait.
Yes, Anne-Marie, say it. I saw you. Goodness.
I said it's gonna get smaller.
It's going to get smaller and smaller and smaller, right? What's a half times 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 a half? It's going to get smaller and smaller and smaller. So this highlighted portion actually goes to 0 and leaving you with a over 1 minus r. That should look familiar. Like that, you guys have definitely learned that in like pre-calc or something. That's where this comes from. No? Maybe?
Yeah,
no?
Okay. I feel
John,
so.
I have no idea what you just did in the last 15 minutes. Okay, so let me just summarize here, okay? If you have a geometric series, right? So if in the form and R is, the absolute value of R is less than 1, meaning you're only dealing with 0 to 1, not including 0 to 1, then the series converges. Oh my gosh, converges to
0
equals a over 1 minus r. If you didn't pay attention in the last 10 minutes, this is the one thing I want you guys to learn, okay? If you're given a geometric series, if you're given something in this form, and you know that, so you're checking for two things, and you know that the absolute value of r is less than 1, then you know the series converges, and on top of that, you know what it converges to. And that's kind of important because with geometric series, this is the only like test that actually tells you what the series converges to. The next 6 or so tests that we learn, yeah, there's that many, are not going to tell you that. They're not going to tell you what they converge to. They're just going to tell you if it converges or diverges. We'll talk about that later on though. But for now, you should know, you should learn how to find the sum of geometric series and tell me what the series converges to.
So a geometric theory will always be in that format, right there. A to the r, okay.
A times
So
r
like
to the n. There's always going to be something in parentheses raised to the n power with a constant in front. Or like there's always going to be a way for you to like rewrite it.
Okay.
Okay. Why don't I do a quick example? Really quick example. I know I'm running out over time. So let's say this is example, I don't know what example we're on. Let's say we're doing, this is on page 516. So let's say we're looking at that.
Mhm.
right? At first glance, it may not look geometric.
1 times.
At first glance, it may not look geometric, but I can rewrite the inside as 1 over 5 to the n. Oh yes, by the way,
Yeah.
exponent rules are going to be very, 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 very prevalent in this section. And I know that doesn't seem hard at first, but it's I don't know how else to explain it. Make sure you know your exponent rules really, really, really well. Okay? I warned you. All right. So look, I have a geometric series, right? So for me, you need to state 2 things for you to jump to this thing, a over 1 minus 1. For you to use that, you need to state 2 things in your work. You cannot just jump to this and be like, oh, the answer is 1 over 5, right? Like you can't do that yet, okay? You need to state 2 things in your work, okay? You need to state, this is a geometric series where a is 1 and r is 1/5. That's the first thing you state. The second thing you state is, since the absolute value of r is less than 1, now you can say that. Do you see what I did there?
Yeah.
And not just jump straight to your answer without explaining how you got there. That's going to be kind of like a recurring theme in these next.
And then you could do
lectures.
the opposite for when it's greater than 1. Like you just put like, since this is a geo series, and since our absolute value r is greater than 1, diverges.
Yes, then the series diverges. So you would say, so for this case, since this, you get, what is this? 1 over 1 minus, whoops, that's 4/5, which is 5 over 4. So the series converges. Okay, so the series converges to 5 over 4. So this is, I know it's a little sloppy, but this is sufficient work. All right, no more, no less.
Okay.
Any questions? I'll do another like geometric, a harder one example in the video. Right? But once again, for now, recitation tomorrow, it should mainly be the review for the exam. And I don't know if she's gonna do the polar stuff with you guys. I'll check in with her and ask her what she's gonna do. Right? But if you guys want to stick around, ask me any questions, by all means. Otherwise, I'll see you guys on Wednesday. Please study, please study, please study, please study.
I also have a question.
Yeah.
See you, John.
Yeah.
See you, Handel.
The question I was gonna ask is, are we gonna be able to? Are we gonna, like, in this class? Are we gonna be creating, like, in my calculus class? I remember when we were going over the sequences and everything and all that. I don't know, created like formulas. Like we had different formulas and we have different things that we just had to create formulas, like how you did for the a over 1 minus r.
Okay, I'm not sure if this is what you're asking, but so geometric series is it's a specific type of series. There are a bunch of other types of series out there, and we are going to learn how to kind of test for convergence or divergence for those series. Kind of like with integration, right? You learn first how to like integrate like one case, the power rule, right? And then you learn different rules for different scenarios. That's what we're going to do with series. So we just learned a specific scenario. We're going to learn more scenarios in the near future. Does that answer your question?
Yeah, I believe I answered my question. Yeah.
It's going to get crazy, man. Anyone else with questions before I end today?
Thank you, John. Have a great day.
See you, Ali.